Sorry about that. I almost didn't start the recording. Okay, so we just looked at Morse code and we came up with a statement, 2 weeks left, number of weeks left in class. Okay, and we're going to go through and count the number of letters. It's 12. The number of dots and dashes. No, 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13,
I think it's
28.
27. Oh,
27.
28.
I'm
I
okay with
can't.
either one of them. We'll go with yours, 27. How many spaces? 1, 2, 3, 4, 5, 7, 8, 9, 10, 11 spaces. So that's a total of, oh my, that's a total of 38 characters, 11 and 27, to get a 12 letter message. So that's averaging 3.1. Yeah, the average
It,
character length. It's going to
it
take,
is 28. You were right. I
oh,
recounted.
okay.
Mhm.
I'm glad you're counting with me. So 28 and 11 is 39. 39 divided by 12 is 3 point, maybe 2. But you see, I got this whole mess, and the big problem here is, these aren't too bad, but when I start throwing in those extra spaces, I definitely have trouble. All right. So what we're going to take a look at today is this whole idea of left and right and binary tree. And we're going to do something where, what if I wanted to get a message and it's immediately decodable? I don't need the spaces in it. If I could do it without spaces, with dots and dots and dashes, and all of a sudden, I'm going to be able to send a faster message. So let's see how this works. Let's say I went, and hopefully you watched some of the videos and you got some idea here that I went through a book and I counted 20% of the letters were A's, 10% of the 10% of the letters were B, 10% of the letters were C, 15, and that should add up to be 100% of the letters. It's a new language from somewhere. Okay. And let's say my A, just like my Morse code, I had it set up as something that looks a lot like this. Um, I am missing something. Okay, I'm gonna pause the video. I'm missing something. I'm sorry for the recording. All right, so let's say I came up with some letters, some combinations here, and based on, first of all, the percentages of how many times the A occurs, the B, the C, and so forth. I say, okay, oh, look what I just did. I came up with some letters, and if I wrote this down and I went something along the lines of this, is that immediately decodable? So what I'm trying to do is figure out a way that I can give you a message so that that average character length comes down. That's my first goal. I want to lower that. I want to be able to get rid of the spaces, but I also want it to be decodable. Okay. So if I wrote this, are you able to figure out what my message is? Because I don't have spaces in there.
Is it cab?
Is cab. Okay. And if I looked at this 2, 4, 6, 8, 10 divided by 3, okay, that's not too bad. That's a little bit lower than the 3.2 from up above, but we're going to work on getting that to be a little bit lower and lower. So right now, I can actually, and I just said this is 3.1. I can come up with something that's going to be called the expected length. And the expected length is going to come from, well, if A is 20% of the time and there's 2 characters, okay, and B is 10% of the time and there's 4 characters, but that's a 1, and C is 10% and there's 4 characters, and D is 15% and there's 3 characters, and E is 45% and there's 1 character. This is going to help me with my expected length. I'm going to be able to say given this, I want to create something that, like I said, is immediately decodable, but also has a small expected length. So this guy becomes 0.4 plus 0.4 plus 0.4 plus 1.5 plus 0.45. So that's 1.2, 2.7, 3.15, if I did my math right. Well, that's not too bad. I'd like to get possibly something a little bit lower than that as well. So, question now is, if I'm given these percentages I went through and counted, I need to create this again so it's immediately decodable. I can get rid of those spaces, and the average expected length is pretty low. Okay. All right. So the way we do this is we create something called a Huffman code. A Huffman code. I had notes all over the place. Now, here's how a Huffman code works out. It's going to look like a tree, but instead of starting at the root, we're going to start at the bottom and work our way up. Now, from the video, what are the first two letters you should probably use here?
Is it the smallest ones?
Yeah, the smallest ones. And the smallest percentage ones are the ones that are used the least, which means they probably should be kind of on the bottom. Okay, so we're going to start with that. We're going to say here's a 0.1, here's a 0.1, here's B, here's C, and they're going to combine to make a total of 0.2. So I took care of this and I took care of that. Now, keep that idea in mind. The smallest ones, well, let's see. 0.15 is pretty small. So that's going to definitely be 1. And now I have a choice, either this combo or the A to keep working. Well, I'm going to do the A, and the A is just being introduced, and the D is just being introduced, and the A is 0.2, and this is 0.15. And when I combine those, I get 0.35. Okay, I got rid of that, I got rid of that. Now I have 0.25, 0.35, and 0.45. Well, I said join the smallest two. That would be these two. That gives me a 0.55. Well, I'm left with my E, and that was a 0.45. So by way of Huffman codes, I'm now going to combine those and make that a 1. Huh. Where's he going with this? Well, I built that tree. So my first question is, do you understand how that tree was built? Yay or nay? See,
Does it
Austin's
matter
in
like
there.
what order we put it in? Like we put D before A or
Nope. And so when, they were passing messages back and forth during the war, this was part of what made it really difficult. I could give this list to you, and there could be several different answers that come out. Like I said, the next step would have been to combine the D and the 0.2 instead of the D and the A. I could have switched locations. This could have been C, this could have been B. Because what I'm going to do now is down the left side, I'm going to put a 0. Anything down a right side, this is another left side, is going to be a 1. So what I now come up with is 3 digits, 2 digits, maybe 1 digit for each letter. My B, 000. My C, 001. My A, 010. My D, 011. And my E is 1. And if I wanted to find the average length, I would take 0.2 times 3 plus, and plus. But let's see if this made something that is immediately decodable. All right. Let's see what I got. Is that immediately decodable?
Yeah, it is.
Yeah, what do you get?
Is it ace?
Aced. ACED. Yep. Let's see what I got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 divided by 4. My average length is 2.5. Is this better than Morse code? Yeah. Man, that would really be hard to decode without this guy. This stuff is actually kind of cool. Actually, kind of cool, in my opinion. In my opinion. All right, I have another one. I'm going to put you in groups after I pause this record. Sorry,
Would you
Carl.
have ordered it in a different way?
Could you have? You could have switched C and B.
Would you have?
Um, I would have probably, after B and C, that being a point one, I would have connected that to F because they would have been the two smaller ones. The point one is less than the D, which is point two.
Okay, I got you.
Okay. Somebody else have a solution?
We just did like we're still doing the tree, but we didn't got to the to the code for the numbers.
Okay, can you show me what you have so far?
Slim, can you show sir? Because you
Okay,
had it.
if I
Do you have it, Slim?
I don't know why it's asking me to sign in to right, but
Carl, any hints on how to show the whiteboard? Just do share.
I didn't show my whiteboard. I took a screenshot of it because I'm pretty sure it just deletes once you leave the room.
Idea. Now I can tell people to do that. That's probably why Slim can't share. But taking a look at it, just for kicks and giggles, we could have done C, which is 0.05, F, which is 0.05, and when they combine, I'd get a 0.1. So I took care of F, I took care of C. And this is what I said I may have done and probably should have for best results, took B next and made this 0.15. So that knocks those out. Now I have a 0.3, a 0.2, and a 0.35. Probably would have done the 0.2 next. I could put it just about, I could put it over here. To combine with this, I could put it over here, just the way the page is laid out. That 0.2, that gives me 0.35. So now I have a 0.3, a 0.35, and a 0.35. I may have done this next. A is 0.3, E is 0.35, 0.65, and then 1. And then, of course, going down, zeros and ones. E would have been 111, A would have been 110, that kind of deal. Okay, good. 000. C is 4 zeros. 1, 2, 3, 4. The higher percentages, as you can see, are less digits. Questions? And again, what do we have here? A binary search tree, right? The binary tree going left and right. Are we using it for searching? Kinda. We're searching for the letter C. We're searching down a path, but still working this binary tree. And we're going to do another thing yet today with binary tree. And then we're going to be starting to do, or the last week, something with just a generic tree. And that's a little bit bizarre. Okay, second thing is this thing called tree balancing. And if I had a tree, a binary search tree, and it looks something like this, D, E, F, G, H. That wouldn't do much for searching, would it? It's not laid out very well. It's not like, wouldn't it be nice if I could just get some of that over to the other side so that instead of worst case scenario, 1, 2, 3, 4, I could maybe have worst case scenario of 2 or 3, something that might work out a little bit better than the 4. Well, these guys, Adelson and Belsky Landis, came up with something called AVL trees. And this is a way that we're going to balance a tree. All right. Now, balancing a tree, we're going to need to work with a balance factor. And what's that balance factor? That's going to be the height of left tree minus height of right tree. Okay? And we want those numbers to be -1, 0, or 1. All right, so we're going to use this example first. And I'm going to build a tree with these numbers. And I want to make sure that I always have that balance factor of one of these 3 numbers. If I don't, if it becomes 2 or 3, then I'm going to figure out a way to balance my tree so that it doesn't get all wonky like this. And it's not an efficient search tree. So they're taking our search trees and they're making them better. All right. So let's start with this number one. It's going to be a little bit easier to work with. And the first number I put into my tree is 14. That's all good. Second number is greater than. It's 16. Now, before I go anywhere, I want to know what the balance factor is. For 14, it's the height of the left subtree, which is 0, minus 1. So right now, this is 0 minus 1. That's a -1. This guy is 0 minus 0. That's 0. That's a pretty good tree to look at. The left subtree minus the right subtree. All right, I'm going to put 4 in. 14, 4, and 6. Still pretty good. This is now 0, 0, and 0. I'm going to add 8. 8 is, hold on, Bubba, that's a 16. My apologies. 8 is less than and it's greater than. If I check my balance factors, I think I'm still okay. This one would be a height of 2 minus a height of 1 is 1. This one would be -1. And of course, any of these guys are going to be 0. All right, let's keep adding numbers. 14, I have 4, I have 8, I have 16. So 14, 16, 4, oops, looks like I've I did 8 before 6. Okay, now 6. Less than, greater than. Where is the 6 going to go? Down here, right? Uh-oh. This now becomes 3 minus 1 or 2. This is 0 minus 2. That guy's a negative. I got problems all over the place. My balance factors aren't going to work. So now something has to happen. What's going to happen? Well, one of 4 things. And this first thing is called a left rotation. And what it's going to do is, and again, I want you to understand how this works in the simplest forms, coding it, oh man, I can't imagine how they came up with a code. The number of examples they probably went through were probably hundreds and hundreds till they figured out, well, this is a 2 and this is a -1 and da da da, what to do. But this guy right now is going to do a left rotation. A left rotation. And what's going to happen is I'm going to rotate this around so that 8 moves up. Okay. So I'm going to do a left rotation. I now have 14, 8. Okay. 4 is less than, but the 6 has to reconnect. And when I do the rotation, whatever is down here is going to go and connect to the right of a left node. Oh, it's going to go and connect here. It's going to go and connect here. Ah, well, this is still not good because this guy is 1, 2, 3 minus 1. He has a balance factor of 2. So now I need to do something called a right rotation. And when I do that, 8's going to rotate up. I still have the 4 to the left. I have the 6 to the right. When this rotated up, the 14 goes there and the 16 goes there. This ends up being the combination one. This is the left-right. Sometimes just doing a left or sometimes just doing a right takes care of the problem. But here are going to be my 4 choices for rotations. A left, a right, a left-right, or a right-left. But now I'm balanced. Next number to add is 10. It's greater than, it's less than. 10 goes here. Yeah, this is starting to look pretty good for ever popular searching through the list. The next number is 5. It's greater than, it's less than, it's less than. Balance factor. This guy's balance factor is -1, -1, 0. 2 minus 1 is 1. That's a 1. That's a 0. That's a 0. That's a fairly efficient search tree. So I'm either going to do a left, a right, this thing called a left-right, or a possible right-left. All right. So now we come up with this guy. All of these states. Okay. I'm going to put you in a group for 5 minutes. See if you can start on this. This is not easy. This is not easy. But I want you to see where the mistakes are so that when we do it, we can see what the mistakes were and how to correct them. So let me pause. Okay, we have everybody back.
Yeah, I think so.
Okay. Oh, look at me. I did the first 3 for you. So after the first 3, did you run into trouble?
Oh yeah, because you'll have to rotate here.
We're going to do a right rotation and we'll do it on PA and we'll have something that looks like PA. Oh, should be a D. Delaware and Rhode Island. Very good. It's a balanced tree. I had a factor here of 2 that needed to be fixed. All right, Georgia, less than P, greater than D. I think everything looks okay there. Questions? Ohio, O is less than P, greater than D, greater than G. Do I have a problem here?
Yeah,
Yeah. What do I need to do?
rotate Georgia.
Rotate Georgia. Okay. Yeah, this is a little better example than that other one. This is working out pretty good. There goes Georgia. There goes Delaware. There goes Ohio. And over here sits Rhode Island. Starting to get the idea? Should I keep going?
Yeah, go. Keep going.
Okay. Massachusetts, less than M, greater than G. Okay, Massachusetts is gonna go here. Yeah, I have a factor here of 2. So because I added Massachusetts, something's gonna have to happen with Ohio, and what happens?
It rotates left.
It rotates left, and then what's gonna happen?
Georgia has to rotate right.
Yeah, this is gonna rotate left. So Ohio is gonna be there. Whoops, Georgia is gonna go down. Delaware is still down. Massachusetts is going to have to connect onto the right of Georgia. This has to connect. Okay, so there's PA, and down here is Rhode Island. Yeah, and now I'm going to have to do a right rotation. That's going to bring Ohio up. I'm going to have Georgia, Delaware, Massachusetts. See, I rotated around. Here's PA, and Rhode Island was to the right of PA. Now my balance factors are good. I added Massachusetts, and I could keep going if I want. It's in the book. It's in the NIOF book. So if you wanted to walk through it and look at it with a different approach or keep going, or like I said, the full video is available to watch with coming into class. But hopefully that ties up any loose ends you might have. Any questions?